For our Henry's Law example, we're going to compute the equilibrium mass concentration of oxygen in units of milligram per liter for water exposed to the atmosphere at sea level at 20 degrees Celsius. We're given Henry's constant for this temperature, and we're told to assume the mole fraction of oxygen in air is 21%. Okay, so what we're looking for is the amount of dissolved oxygen in the seawater. Okay, so if we look at our expression for Henry's Law, we have one that relates aqueous concentration to gaseous concentration expressed through the partial pressure, and vice versa. Since we're looking for the aqueous concentration, let's go ahead and use this first form. So that means concentration of oxygen is going to be Henry's constant at this temperature for oxygen times the partial pressure of oxygen. All right, we're given this. This is what we're trying to find, but we don't know what the partial pressure of oxygen is immediately. So let's look at what other information we are given. Basically, we've used everything else except this fact that the mole fraction of oxygen in air is 21%. So that's a pretty good indication that we should be doing something with this piece of information. And if you remember back to the first week of class, we know that the mole fraction of some component of a gas is going to be equal to the partial pressure of that component divided by the total pressure of the gas compound. Okay, so we can rearrange this expression. Partial pressure of oxygen is going to be equal to mole fraction of oxygen times the total pressure. And again, we're given this, YO2, that's the mole fraction. And now what do we think about this total pressure? Well, we know we're dealing with air at sea level. We're dealing with the unit of atmosphere in our Henry's constant. So that means the total pressure of the air at sea level is 1 atmosphere by definition of what an atmosphere is. Okay, so we actually do know this. And then for step 3, we can put this all together. So the aqueous concentration is going to be equal to Henry's constant times mole fraction of oxygen times the total air pressure. And if you plug in all these numbers, you should get a value of 2.9 times 10 to the minus 4. Now let's think about units. So this is in moles per ATM. This is unitless, so I'm just going to put 1. And this is in ATM. So that means ATM cancels with ATM, and the units of this are moles, which is exactly what we want because we're using the brackets, right? And brackets denote molar concentration. But what does this problem ask us for? It asks us for the concentration in units of milligrams per liter. So what we need to do in order to convert from a molarity to a mass concentration, we have to use another relationship from week 1, where the mass concentration is equal to the molecular weight times the molar concentration. Okay? So that week 1 stuff actually means something in this class. And what we find, so we just have two little molecules of oxygen, and oxygen has a molecular weight of 16 grams per mole. So this is going to be 2 times 16 grams per mole times 2.9 times 10 to the 4 molarity, which if you remember is moles per liter. So this gives us the concentration in grams per mole, but we need to convert grams to milligrams. And then if you do that, you'll get the final concentration is equal to about 9.3 milligrams per liter. Okay, so I didn't show every step, but I'm assuming you guys can do grams to milligrams on your own time.